All right. Since you folks are far enough, is it okay if I take the mask off? Yeah? Okay. All right. So we have had an awkward start to this in-person lecture, but let's see how this goes. All right. So today we are going to talk about programmable interdomain routing, and like this is a good connection, a good pivot from what we were learning in terms of virtualization, because this is a now we are transitioning to the phase of this course where we are going to talk about applications of different building blocks for the programmable networks that we have learned so far. In the last lecture, we were talking about network virtualization, and this is an application of software-defined networking in context of interdomain routing. So what is interdomain routing? We'll learn about it. Why programmable networks are required, or why software-defined networking is required. There we'll talk about it. And we'll also talk about, or we'll revisit some of the concepts that we learned before, especially we'll learn something, or revisit the virtualization concept here, right? So, so interdomain traffic control. Give me one sec, I think. So how many of you know border gateway protocol? Did we cover that in 176A? Okay, can anybody tell me what border gateway protocol is? Yeah.
The protocol handles routing through two ASs.
Okay, how does it work?
Each AS posts which routes it controls to the other ASs, and
yeah,
it propagates across.
Okay, okay. So basically, if we take this example, we have three different networks we're talking about. We have Google, Level 3, and Cogent. I'm just using these, names for our understanding. And the participants can be Cogent and Level 3, which are, why is this? Anyway, so the participants here can be peers of Google, and they can be advertising their routes. And basically here, we are going to see that each of them have an advertisement of a particular IP prefix. And when they're setting up a peering session, which is key for border gateway protocol, that each of these participants are setting up a BGP session where they're exchanging routes with each other. So in this case, Cogent and Level 3 are advertising that, hey, I have a route to this IP prefix 10/8, right? And maybe quick check on our basics of networking here. So can anybody tell me what 10/8 really means here? What does an IP prefix 10/8 means? Yeah, go ahead.
Is it like last 8 bits are they all belong to that? Like they control all of the last 8 bits. Okay.
Yeah, so we can think of so this is almost correct with some minor mistake, but when we think of IP addresses, they are 32-bit addresses, right? And when we say that 10/8 or any slash, basically we're talking about a prefix. We are talking about set of IP addresses that are represented by that prefix, right? So 10/8 is actually representing all IP addresses that have the first 8 bits mapping to 10, and the other 24 bits, like any IP address that has the last 24 bits can be anything, but if their first 8 bits are mapping to 10, then this prefix is representing that, right? So it is 10/8. So we are talking about 24 different bits available or within this prefix. So 2⁻24 is the number of IP addresses that it is representing, and it is saying that I know a route to this, all IP addresses that belong to this prefix, I know routes to all of them. And if you have traffic where destination IP address is anything within this prefix, you can send that traffic to me, and I know how to take it all the way to the destination, right? So when we talk about interdomain routing, there can be multiple participants who might have the routes, right? So for example, when we talk about UCSB has actually UCSB only has one provider Then there is one more, but that's a backup provider for us. So, but if there are two peers of that provider, then there will be two participants who will be advertising routes on behalf of UCSB, right? So maybe I can help you visualize what I'm talking about here. Is that if this, I don't know if support, so if this is UCSB, UCSB has one network that it is peer of. So we can say provider, right? And if it has two different peers, right? Provider one or peer one, peer two, right? So now if UCSB has something, 16.2./16, right? I'm just making this up. This is not a real prefix, right? So if this is a prefix that UCSB has, like we have maybe your Ediro IP addresses, we can check what that prefix it belongs to. But any traffic or, like any IP address that is within this prefix, UCSB will, the border router at UCSB will set up a BGP session with its provider. It will say like, all these, I know routes to all these /16 IP addresses, right? Now the provider will advertise it to its peers and say like, I know routes to this /16, and like the routing path is now via me, right? I am one hop in the middle of this routing path, and you can send traffic to me, right? And now, like if Google is peering with these networks, then basically it has these two options available at it, right? So by default, there will be multiple routes that will be advertised for the same prefix for any AS or any like a network. Then it will have some internal policies to decide that among all these routes that it is looking at, what is the policy to select these routes, right? So sometimes the preference can be that what is the whichever has the shortest number of AS hops, right? So what do we mean by AS hops? So this UCSB is its own AS, right? Its own administrative system. And then this provider is another AS, then this is another AS. So the route that will be advertised here will be, like P2, and then, like whatever this provider is, and then UCSB, right? So this is the AS path that will be advertised by this provider. This provider will make similar advertisement, but it will replace this P2 by P1, right? It will put its own name, right? So in this case, the AS path length or hop length is the same, right? So then it will, like, Google will apply its own policy of preferences that, like maybe it is paying less to this peer or, provider. And then maybe for most of the traffic, it will prefer P2 over P1, right? So these type of policies are intrinsic for BGP. And this is how inter-domain routing works. Questions?
Cover the subnet mask. Yeah, I was always under the impression like 192.168.1.1 or like 0.1/8 being the last point something was the subnet.
So it like basically /8 is indicating that the first 8 bits are the same, and 32 minus whatever that /8, like so 24 bits are the set of IP addresses or set of like bits that are within this domain, right? So we have like you have these hierarchy, right? So you have say 0, which is like nothing, and then you have /4, then you can have /8 within that. So /4s will be like first 4 bits are the same, and remaining 28 bits can be anything, right? So all IP addresses that have the same first 4 bits will belong to a particular /4. And similarly, all IP addresses that have the same first 8 bits will belong to that /8 prefix, right? So smaller is the prefix length, which is 8 of 4. More IP addresses will be represented by that prefix, right? So more specific that prefix is. So /32 will be the most specific, right? It will just represent one IP address, and /24 will represent like 2⁸, what is that? 256 IP addresses, and so on and so forth, right? So this is how prefixes work, and border gateway routing is all about advertising these prefixes and advertising the routes for these prefixes, right? Okay, so you can see the screen, right? So basically right now, or when we say that the current interdomain traffic control, the advertisements are made at the granularity of IP address, and the decisions are also made at that same granularity, right? So the argument is that this is a bit inflexible, right? I might have some very specific policy that I want to apply and say like, okay, all HTTP traffic should be treated one way and non-HTTP traffic should be treated the other, right? And if I go with this conventional view of how interdomain routing should work, I might not be able to apply that policy in place, right? So this is where, like we have, or this was kind of like the state of the affair, I would say 8 years ago, right? When this whatever topic we are going to discuss, like these set of ideas emerged in 2014, 2013 timeframe, and this was the state of the art back then, right? And there was this growing demand that we need more flexible control over how we are routing traffic on the internet, right? So, for example, if Google is the network operator that we're talking about here, go ahead.
Are you sharing your screen?
Oh, is it not shared? Okay. Thanks for pointing out.
Yeah.
All right. Is it visible now? Okay. So, like this is for your clarity, this was the figure that we were looking at before, that we have these three networks, Google, Level 3, and Cogent, and each of them are advertising 10/8 prefix. And then the decision that the Google is going to make is at the granularity of that IP prefix, right? So all traffic that belongs to this prefix will either go to Level 3 or Cogent, right? And I'm arguing that this is a bit inflexible argument. So I hear my echo. Anyways, all right. So moving on, there is a case for flexible interdomain routing that as networks are becoming more and more complex, there is a growing need for the networks to express more flexible control policies for how their traffic should be routed in the internet, right? One example here is that Google can say that, okay, for YouTube, given that it's it is very sensitive from quality of experience perspective, I think Level 3 must be, I'm paying more to Level 3 and it is offering me better quality of service, then I will make sure that the video streaming traffic goes through Level 3 and all the non-video streaming traffic goes through Cogent, right? So this is an example of a flexible policy that Google might want to apply. And also if there is an attack traffic coming in, which is a DDoS attack to your network, so rather than waiting for the traffic to come to your own network and then applying the mitigation policies, you can push your policies up in the network and say like, okay, if there is an attack traffic coming to my network, block it as close as possible to its source, right? So I might want to propagate that information as far as possible from my own network so that my network doesn't get overwhelmed, right? So these are just examples of why we need, or why there was a need for a flexible interdomain routing. Okay. So now let's go back to the basics, like close to what I was discussing here, that when we have two entities that are trying to exchange routes with each other, they will first, their border routers will have a physical connectivity with each other, right? And then they will set up a control protocol called, as we know, Border Gateway Protocol, and that they will establish a BGP session, right? Once they establish a BGP session, then they will start exchanging routes. That Google will say like, okay, I know routes to these IP prefixes, which are basically Google's prefixes, and Level 3 will basically advertise the entire internet's routing path to Google being its provider, right? So now what happened over time was that since there were, more and more participants who wanted to connect with each other, a logical kind of like consensus among the community was that like, okay, you want to peer with Cogent, you want to peer with Level 3 and maybe hundreds of other participants. So rather than having these, specific locations where each of us will peer with each other, why don't we all go to one location where our all border routers will be co-located with each other, and that will save us a lot of money, and we can just have one location where we just exchange routes with each other, right? So that is a very oversimplified reasoning for how the internet exchange points came to being. But in different areas we have different types of models in place. In some cases, there are these peerings are open, and the internet exchange points are public exchanges, so you don't really pay a lot. But then there are these private co-location points which are offering you a lot better service in terms of packet drops and like other QoS services. So there are different types of models in place, but the key essence is that what internet exchange points brought to picture was that they provided a layer 2 fabric or a switching fabric, which will be used by all the participants. All they need to do is just bring their device or border router to that location and then plug that in, right? And make sure that you have, of course, connectivity to your own network from that border router. But once you have that, you just have one co-location point, one location where all these routers are located and they're physically connected to a switching fabric, right? So this is the concept of internet exchange points. And this is important, like, it's important to understand that rather than like, if you want this flexible control, right? So one approach can be that we can consider replacing these border gateway protocol like BGP routers itself, right? So maybe we can say that, okay, all these networks should just replace their BGP routers with something which is more programmable, right? Like open flow devices. That can be an approach. But think about it, there are 65,000 plus networks. And if we argue that each and every network should just replace their existing routers, which at that time were order of millions of dollars. So we are talking about a very, very expensive route to go and enable flexible control or like flexible control over the routing traffic, right? So in that context, this IXPs are actually very interesting because they're strategically located. If you make change at one IXP, then you are actually enabling change for hundreds of participants that are present there, right? So from that location, these IXPs actually became interesting strategic locations where we can think about bringing this software-defined networking ideas and making changes to the interdomain routing, right? And it is important to get the context here because the ideas of software-defined networking or ideas of having some type of flexible control over interdomain routing has been there since inception, right? So BGP is like, came out in 92, 93, and within 4 or 5 years, networks are like, no, we need more flexibility. And what they started to do in like, around that time, software-defined networking didn't exist. The kind of like the abstraction that we read. So what they started to do was that they started adding more complexity to the routing policies, right? So they created new daemons and basically they were saying that, okay, like now we are going to support these new VLANs and those VLANs will have these specific policies. So they were just trying to add more and more complexity to the existing set of border gateway routers that were out there. And they were just bloating the requirement that each of these ISPs had from these BGP routers, right? So over time, most networks were in one way or the other supporting, running around different types of hacks to get this flexible control. But they were just at the end of the day, they were just buying more and more expensive routers to enable that control. And even more important was that around that time, failures were very common because people were pushing so complex configuration that like in their entire network, there were maybe just 1 or 2 person who might understand what those configurations really mean, right? So those configurations were very, very brittle and the failures were very, very common around those times, right? So, there was this tussle that there is a need that we need flexible control, but the solution didn't really exist, right? So then the researchers started thinking about what can we do? What can be a more feasible way of bringing this change? And, this is 2013, 2014 timeframe when the ideas of software-defined networking in context of data center networks are already there. But applying those ideas in context of interdomain routing was actually very challenging. And internet exchange points in that context is very strategic location, because if you bring some change to that exchange point, you're actually affecting or influencing all the hundreds of participants that are present there, right? So what, when we look at these exchange points over time, when exchange points started, it was maybe 3-4 participants that were coming in, and it was very easy for them to set up one-on-one BGP session with each other, right? So Google comes in, there are 2 other participants. It all needs to do is like set up 2 more sessions with these participants. And over time, when more participants came in, they will just set up more sessions, right? But then after a while, it became a bit unsustainable, right? So when you have hundreds of participants, then each BGP router has to set up hundreds of different BGP sessions with all the other participants out there, right? So that just bloated the control plane complexity, and the community came up with a solution called route server. So the concept of route server is very simple. In route server, rather than setting up a BGP session with each and every participant, you just set up a BGP session with route server, right? So route server is just, accumulating advertisements from all the other participants and then sending you a filtered view of those advertisements, right? So that it just simplified it. You are just offloading that BGP decision making to that route server, and that route server is just advertising or forwarding you the filtered information. And that's how they were significantly, like, they were game changers when as internet exchange points were exploding. So route servers were very, very critical because they were making sure that, every participant just has one BGP session, right? That said, route server, like, something to note is that not everybody was happy with route server, in a sense that, like, not all participants were coming to exchange point with the mindset that they will just, like, let route server make decisions for them. So sometimes, for some critical traffic, say for example, if an ISP is peering with, say, Netflix at that time, so they would set up a session, different, like peering connection with Netflix, and use this common switching fabric or the public switching fabric for the non-critical traffic, right? So this was kind of like the state of the art, that participants come in, they would usually prefer this public fabric, which is a shared switching fabric across all the participants for non-essential traffic. And then for essential traffic, they had these private peering sessions as well, right? Any questions so far? All right. So the idea of software-defined exchange points here, in context of what route servers was doing, was very simple. That they said that let's, rather than using a old school switching fabric, why don't we replace that with a programmable switch that can be programmed through OpenFlow, right? And recall this is 2013, 2014. So OpenFlow was the only program, like, interface that people knew about as a software-defined networking interface, right? As we have learned recently, that the PISA targets are new set of data plane targets out there, and there are these different APIs that are also out there. But around that time, OpenFlow was the like the most dominant API, southbound API that everybody was using, right? So replace that conventional switch with a programmable switch, and then replace that route server with an SDX controller. So now this SDX controller is not only making decisions for the default routing that you have to, like default routing decisions, but it will subsume those decisions and add more, flexible decisions that you want to apply on the traffic, right? And again, I think the session-wise participant just has to establish a session with the SDX controller, like it was doing with the route server, and like there is no additional complexity here. So if you think about it this way, that participants are now able to get flexible control without changing anything from their infrastructure perspective, right? So they're still using the border gateway routing. They're using the same BGP router that they were using before. It's just that they're setting up a new control session with an SDX control. That's it, right? And the IXPs were more than happy to embrace this type of model, because now they were able to, market themselves and differentiate from their competitors, saying like, okay, like, if you come to our switching fabric, then you actually get flexible control, right? So it was well motivated from both stakeholders in this context. Now that we talked about the high level overview of what SDX is, like building such an SDX that works in production settings is a very challenging game, right? Like, talking about these ideas in principle is very different from deploying them in production. So the first challenge was the programming abstraction itself. And we have been talking about programming abstraction for some time, that, like abstractions are the key for software-defined networking. And even though it might look very straightforward that it's just one switching fabric we are talking about, but there are nuances that one has to take into consideration when we talk about these SDXs, right? So how, like, what is the view of the network that we should expose to these participants that enable them to express their flexible control policies without worrying about what the physical infrastructure is, right? This sounds familiar. This is very similar to what we learned for virtualization as well, right? So rather than exposing this physical switch to these participants directly, we have to come up with some new virtual view, abstract view, so that they can express their control programs, right? So this has a lot of similarities to the NVP that we read earlier. And then something new about these software-defined exchanges is that they have to interoperate with BGP. We saw that BGP has its own set of, like like protocol in place, and there are these rules that have to be followed. And if those rules are violated, then there are consequences, right? So when we are enabling this flexible control, we have to keep in mind that all this flexibility is only at the exchange point. The world outside this exchange point is still using, old school routers and old protocols in place. So if we are not compliant with those protocols, then we might be losing all the traffic which we are sending in name of flexible control, right? And then, like all this framework has to scale for hundreds of peers that are going to be present at the exchange point. It has to take into consideration that there will be more than half a million prefixes that will be advertised at this exchange point. And you are talking about flexible control, like matching on multiple header fields concurrently, right? So overall, I think in general, though in principle, software-defined exchange is very straightforward problem, but like it has these challenges that one has to resolve, right? And we'll talk about what those challenges are. But before we jump to the challenges, so far is the motivation why we need an SDX, the concept of route server, concept of exchange point. Is that clear? Any questions so far?
Argument that exchange points and software-defined exchange points meant to replace BGP?
No. So eventually, maybe yes, but the immediate goal was to stay compliant with BGP, but still offer this flexibility, right? So again, I think the eventual goal should be to replace BGP for a lot of reasons. But if we set that goal, then we will be, we can write a theoretical research paper that what if we don't have BGP and what if we have a new protocol in place, but that will not be a practical solution, right? Because everybody has already invested billions of dollars, supporting or buying devices that can support BGP. So you're like arguing that you should just throw that and use something that we are proposing is not a good idea, right? So like I would say like from that perspective, you can think of SDX as a bit of an incremental change, that it was trying to make a change, provide flexibility, but at the same time ensure compatibility with BGP that everybody else is using, right? Anything else? All right, so basically the question is that how are we going to, what type of programming abstraction or what type of switch abstraction we should provide to these participants at the exchange point, right? So we have to take into consideration that similar to the NVP setup, where the physical infrastructure is shared by all the tenants, in SDX concept or in SDX case, the switching fabric is shared by all the participants, right? If I expose the physical switch to each of those participants, we might have problems, and we'll talk about what those problems can be and how we can address that, right? So suppose we have this setup where we have all these three participants and we let them directly program the switch, right? And Google says that when it is under attack, it might want to drop all packets that are like coming from basically DNS packets, right? So if the source port is 53, and it is like maybe it is under some DNS reflection attack, for some time it might want to drop that traffic, right? So if that is the case, and sorry, the Cogent has a policy that if there is traffic coming for port 53, then it should be forwarded to level 3, right? So given this, like now the switch, if we push both these rules together, right, both are matching on source port 53 and both have contradicting action to be applied. Now the switch will be confused that what should be really done with this packet. Should this be dropped or should this be forwarded, right? And the solution is that if, like in general, based on what we learned from the NVP or the network virtualization already, you should have an intuition that exposing that physical network is not a good idea, right? And we should be providing some type of abstract view of the network. Now the question is, what should be that abstract view? Any suggestions? What will be a good abstract view here? Yeah.
Just a link between any two ASs?
Sorry, what?
Would it be just a link between any two ASs, or?
Yeah. So one abstraction can be that we have n number of virtual switches, which are just one hop connectivity, right? Direct connectivity between two participants. It's an option. The only challenge with that is that from a controller perspective, if I'm Google and if there are hundreds of participants, then I have to keep track of those hundreds of virtual switches, right? So I have to write separate programs for each of those virtual switches, right? So that is one challenge. But they can, like, you're headed in the right direction. So a slight improvement of that will be what?
Combine them all so Google only sees what Google's connected to.
Exactly. Congratulations, you have written a research paper. So this was one of the key idea with STX, that basically rather than exposing the physical switch to each of those participants, what if we just expose them a virtual switch, right? So where they are the only participants who can program, right? So they can see all the other participants as the member of this exchange point, but the only participant who can write control programs is Google. Now, under the hood, whatever that virtualization layer we learned is responsible for mapping those abstract decisions that each of the participants are going to make and compile them into the match action table entries that are correct and in congruence with whatever policies each of the participants have expressed, right? And that can lead to some interesting challenges then that we will read later. But overall, at a high level, the abstraction is that STX is exposing a virtual switch abstraction. Each participant has its own view of the network, and it can write programs as if it is the only participant at that exchange point, or it is the only participant who can write control programs there. Okay. Yeah.
These control programs are not implemented through virtual switch, they're implemented through hardware switching.
So like exposure wise, you are exposed to that virtual switch, right? So you will write your control programs as if you are writing that on that virtual switch. Now the virtualization layer that is sitting in between is responsible for translating that into match action table entries.
Which are then on piece of switches.
Or open flow
Hardware
switches.
switches.
Yeah, hardware switches, yes. All right. So now I think so far we understood that how exactly we are going to express our control programs given this virtual switch abstraction that each of the participants are having. Now challenge is that if it was some normal routing decisions, then this will be very, very easy because you just expose the virtual switch. Whoever is writing those policies, just compose them, compile them. That's as easy as it can get, right? But now we are also interoperating with BGP. So we have to keep in mind that even though we are allowing all this flexibility within the exchange point, but everybody outside the exchange point is still using BGP, right? So if we don't ensure compatibility or compliance with BGP, then we might end up making decisions that will just lead to either packets getting dropped or forwarded to locations that you don't want, right? So let's try to understand what that challenge really means, right? So let's consider, you can still see my screen, right? Okay. So let's consider this setup where we have those same three participants at exchange point. The policy that Google wants to apply is that if the destination port is 80, then the traffic should be forwarded to Cogent, right? And I have marked these 10/8 and 40/8 advertised by level 3 bold to represent that by default, the choice that Google will make will be to select level 3. So now this policy or this program is actually overriding the default decision that all traffic will go to level 3. But if the destination port is 80, then the traffic is supposed to go to Cogent, right? This is the policy that Google is trying to express. Now, what is the challenge here? So when I say that we have to ensure safe interoperation with BGP, then we have to make sure that when a packet which is having a destination port 80 and destination IP 50.001, right? When we receive this packet, we want to make sure that this packet does not go to Cogent, right? Because Cogent advertised three prefixes, 10/8, 40/8, and 80/8. The IP address of this packet is 50.001. It is not matching to any of these three prefixes. So if we forward this traffic to Cogent because its destination port is 80, if we just naively forward this packet to Cogent, Cogent will receive this packet and see like, I don't know routing path to this 50.001, right? Maybe it has internally it has a routing path and it might use it, but by default, when it is not advertising, it receives a packet, it will just drop it, right? So if Google is naive about how it applies this policy, then all the traffic that belongs to this 50/8 prefix will just get dropped. Is that clear? Okay. So in short, when we say that we want safe interoperation with BGP, what we want to make sure is that these type of packets, they don't, because they're not announced by Cogent, we should ensure that they're not forwarded to Cogent, right? Now, how can we do that? What are our options? A naive solution can be that for every rule that I express as a flexible rule, I match on all the prefixes that Cogent has advertised, right? So in this case, it has advertised 3 different prefixes, 10, 40, and 80/8, right? So for all these prefixes, I will express a match action rule and say like, okay, destination port 80, and it matches on this prefix, then forward to Cogent, right? So now I am being very specific that on what fields I have to match, and this is actually correct, right? So this is basically what Cogent has advertised. I'm matching on Cogent's advertisement, I'm matching on my flexible policy, and making sure that I'm compliant with BGP, right? So, like, do you all agree that this is a safe policy? Like, it's not violating BGP. Do we all agree? So what is the problem here? Should we just accept the solution and be done with it?
For 5.3, for every rule that's written, we need a lot of match action tables in our hardware.
Right. So just to put numbers into perspective here, for this simple example, we're talking about 3 prefixes, right? But in reality, when we talk about an exchange point where we are trying to learn all prefixes across the entire internet, we're talking about around millions of prefixes, right? So for every rule, we'll have an inflation factor by an order of million, right? So even though this is a correct, like, it is correct in terms of compliance with BGP, but it is a scalability nightmare that every time I write a rule, I have to inflate that by a factor of million, right? Not sustainable. So what can we do? Any thoughts? Any suggestions? What can we do? All right, let's keep rolling. So that leads to the scalability challenge, as we were discussing, that now we have these, like, the challenge is not just that we have thousands or millions of prefixes or 500,000 prefixes. It's also that we have hundreds of peers and maybe hundreds of policies that each of those peers are writing. And all this has to compile in one physical switch that we have in there, right? Now, things have changed in terms of how much capabilities or how much capacity we have for expressing these TCAM entries or match action rules in the data plane. But, like, just to put some numbers out there, supporting 100,000 entries is a big deal, right? If we see a lot of improvements in terms of cost and everything, maybe we can support 1 million entries, right? But million entries, like, all these match action entries that we have in the switch, they have to be placed because we are matching on prefixes, right? So to match on prefixes, you need a memory type TCAM, right? So TCAM is an expensive memory, right? Because it is expensive both in terms of the power usage, but it is also expensive in terms of the cost, right? So, like, for just one policy, I already have million entries to write, so it's already not very sustainable approach. But like, if we take into consideration hundreds of peers, tens of policies or rules that each of them want to apply, we are, like, getting toasted here, right? So overall, I think there is definitely a need for scaling this solution, but I just want to put those numbers in perspective that 100,000, maybe 1 million is an achievable goal here in terms of how many match action table entries we can push. And clearly, whatever we see right now is way beyond that reach, right? Now, let's try to understand that and visualize this. So we have now 2 different types of devices at the SDX. One is the programmable switch that we are placing by replacing the old layer 2 fabric of the exchange point. We have one programmable switch, but we also have the routers of all the participants. So we have hundreds of participants and they have their own routers, right? What each of them are good and bad at is that programmable switch, it can match on all headers, right? So it can match on any combination of header fields and apply flexible policies for you, right? but it can only support order of 100K because it is very flexible, right? So it can only support rules of the order of 100K. Routers, because they are relatively simple in terms of how many bits they need to, like take into consideration when they're making the forwarding decisions, only 32 bits, right? So that gives them a bit more flexibility, and they can support rules of the order of 1 million. And also keep in note, like, so they already have this table in place, which is matching on these destination IP prefixes and making decisions about what is the next hop for these IP addresses, right? So this table already exists, this capability already exists on the router, right? So now, given this setup, the question is that how can we make the best use of programmable switches that we have and the routers, conventional routers, BGP routers that we already have at the exchange point, right? So keep this setup into consideration when we talk about the solution. So the solution is that, though the number of prefixes are a lot at the exchange point, but the number of participants are still limited, right? So, like maybe at a very, very popular exchange point, we're talking about few hundreds of participants, right? So that is definitely much smaller than 500,000 prefixes. So what if we change the setup that rather than trying to match on the prefixes for every rule, what if we match on the participant, right? So we somehow, I'm just setting this up, that somehow we add a metadata into a packet's header, and that metadata should say that, okay, this is reachable via, Cogent and level 3, or depending on the advertisements, right? So a packet is coming in, it has a destination IP, matched to that destination IP, it should have some metadata attached, which should say what are the next hops to which it can be safely forwarded, right? If a prefix is advertised by both level 3 and Cogent, then it should say that, okay, you can safely go to both of them. If it is only advertised by one of them, then it can only go to one of them, right? So just to be more concrete, we are saying that level 3 is advertising 10 and 40/8, and Cogent is advertising both of them, but also 80/8, right? So if the traffic is coming for 80/8, then it will say that, it is safe to forward it to Cogent. If it is coming from any of those two prefixes, then it will say it is safe to forward to both Cogent and level 3. Okay. So I'm not saying the mechanism of how, but somehow if we are able to add that meta information into the packet, then the rule at the switch can be very simple. It can be like, okay, destination port 80. And if the metadata, Cogent is in that metadata, right? So if it has some representation of which participants are safe, it can just match on that participant. If it is safe, then it can be forwarded to Cogent, right? So far so good. Is this making sense that we have now flipped the problem? Rather than trying to match on the prefixes, which are a lot, we can match on participants. Again, take note that the rest, we are talking about participants being less than prefixes, but there are still hundreds of participants here, right? So for every rule, even with this approach, we're talking about an inflation factor by hundreds of rules, right? So this is something which is a thing that we have to take into consideration. So the idea that these researchers came was that they created this new metadata called reachability attributes, and these are the set of valid next hops for each prefix. And when BGP announcements are happening, then they're advertising these reachability attributes to each of the border router, and then border router already has capability of matching on each of those prefixes. So it is just piggybacking on that capability, and rather than just changing the next hop IP address and MAC address to send it to the switch, it also updates the metadata, right? And now how does that work? We can talk about the mechanism later, but the key idea is that it is piggybacking on the capability that the border routers already had, and now it is making sure that when it is matching on that router, it adds this metadata to the packet. Now, when the packet is now coming to the switch, the rules are relatively simple, that it will match on, it will apply the policy and it will match on the participant ID, right? Before forwarding to any participant, like in this case, that when it is trying to forward to Cogent, it will try to match whether, try to apply a match action rule and check whether Cogent is part of that reachability attribute or not, right? Let's be more precise and more concrete here. So we know what BGP advertisement or BGP announcements are made by each of the participants, right? So that's the table on the left. Now that translates into the reachability attributes that each of those prefixes have, right? So 10/8 and 40/8 have the same reachability attributes because they are both advertised by level 3 and Cogent. 80/8 has a bit different because it is only advertised by Cogent, right? Now let's translate that information and encode that information into packets metadata and come up with a very, very simple scheme, right? So assign 1 bit for 1 SDX participant, right? So, like this is a very simple example. So all we need is a 2-bit metadata, right? One represents level 3, the other represents Cogent. So now when the packets are coming in, depending on whatever its destination IP address is, right? So the router before sending the traffic, before sending the packet to the exchange point, it will update the metadata and add, like set the bit to 1 or 0, depending on whether level 3 or Cogent advertise that prefix or not. Okay. So, basically, if we look at these reachability attributes in in simple terms, then each of them are saying level 3 and Cogent both for 2 of them, and the last one just has Cogent, right? So the attributes will be 1, 1, both bits are set to 1 for 2 prefixes, 10 and 40/8, and for 80/8, the first bit is set to 0, right? Because level 3 didn't advertise it, only Cogent did. So second bit is set to 1, the first bit is set to 0. Is that clear? Okay. So now this is actually very, very simple, right? So if I have a rule which says destination port 80 forward to Cogent, I just update that rule when I'm compiling things into the switch, and I say like destination port 80 and metadata *1. *1 means like I don't care about the first bit, but I care about the second bit, and that second bit should be 1, right? And then you can forward to Cogent. So clearly this is simplifying how we express rules at the SDX, because now we just have almost one extra entry into the rules that into the original rule that we have, right? So the inflation factor is almost 1 in this case. Is that clear? How are we able to bring this inflation factor down to 1? Is that clear? What is the key enabler here? Utilizing the border router is 1 because they're already capable of matching on all the millions of prefixes. The second capability is that using these don't care bits, right? So we are able to support this bit mask and explicitly match on an individual participant at a time, right? So now the number of rules are of the order of number of participants to which we are forwarding, right? So in some sense, there is like any rule can only be forwarded to 1 participant, right? So when we are applying this augmented rule, all we have to make sure is that we just add 1 more match condition and say that is the bits for this participant is set to 1 or not, right? So this is fantastic, right? Now we have reduced the inflation factor completely. There's no inflation almost, and we are able to ensure safe interoperation with BGP. So is this the final solution, or is there any problem with this solution? Any thoughts on what can be a problem with such a solution? Note the size of metadata here. So now this metadata has to be slapped on each and every packet that is coming in, right? And if there are hundreds of participants, then we have to add hundreds of bits to this packet, right? And that's going to be problematic, right? Because one, it is going to affect the bandwidth in general because we are adding extra bits to the packet. But more importantly, where are we going to add these bits, right? So should we be adding a new header onto the packet, or should we be reusing some of the existing fields within the packet, right? And this is where the mechanisms are important, at how exactly are we going to slap this metadata into the packet at the first place. So can we add a new header to a packet? Like, do we have that capability? Can we add a new header to a packet? So with pizza switches, we definitely have that capability. You can define any custom layer that you want, and you can add as many bits as you want, right? So if these participants were using pizza switches, that was very easy, right? We can just customize the routing, the control program that they had, and update the packet processing pipeline, update the parser, and make sure that they can add a layer saying that, okay, 300 bits should be slapped on each and every packet, which will represent that, whether this is forwardable or is it safe to forward to a particular participant or not. But we don't have pizza switches. We have those old school BGP routers. So now what can we do? So let's assume that it's not possible. Like, it doesn't make sense to add any new header to a packet, right? Because one, it's going to affect your bandwidth, and two, we have to pay a vendor to enable a support for this new custom layer that has to be added. It's going to be more expensive and also slow, because vendors will take a couple of years before they can update their fixed function ASIC to support that, right? So we have to make that change now. What can we do? Any suggestions? What can we do?
Create a whole new packet.
You can,
packet.
yeah, but how will that solve the problem?
Well, you receive this first running level packet, and then the actual packet itself.
Okay. I mean, that's going to be expensive, and that will require changing the ASIC to some extent so that it can do this new functionality, right? So it is a feasible idea, but it is going to be, very, very challenging to realize, right? Any other suggestions? What can we do? Like, a hint is here is that, are there any fields that we can reuse in a packet? So that goes back to the basics of what do we have in packet headers. So let's start with layer 2. What do we have? What are the fields that we have in layer 2? MAC addresses, right? So we have destination MAC addresses, source MAC addresses, right? And then we go down, then we have the IP addresses, source IP, destination IP, IP options. Then we go further down, then we have the, I mean, it depends on how you're looking at the packet, go down or up. But this is the sequence in which packets will be parsed, right? So think about the MAC addresses, right? Why do we need MAC addresses? What are MAC addresses telling us? Right, it is telling us the hardware destination. Layer 2 is a protocol, or is the frame that is used for taking the packet over one link, right? So it is the MAC address or the hardware address of the other side of the link, so that the packet can go to that particular destination, right? So the way it works is that you have an IP address as a destination, right? That is the ultimate destination where you want, or like the end destination that you want to reach. But in between, you have these hops, right? Routing paths. So to go from one link to the other, you need to know that, okay, like the routing table will tell you the next hop IP address of the device, right? So maybe we can try to visualize that, suppose this is the modern router, and this is the switch, right? And this is the other border router. Okay, let's call it R1, let's call it R2, and let's switch. So if there is a packet that has to go to R2, or well, not really R2, let's maybe break it down further, right? So what we will have in this R1, let's assume that there is this packet which is coming in at this R1. What will go through at R1, right? And let's keep track on time as well. I think we are running, we probably won't be able to finish everything, but I just want to make sure that we understand the basics here, right? So we will have a match action table in the router. Like this is not a programmable switch, but still there will be some abstraction similar to match action table where it will be matching on some field and making decisions or like, applying the actions, right? So because this is an old school router, so it will only be able to support like match action table, which is matching on the destination IP and then making some decisions. And it, like the decisions are very simple. The decisions are next hop IP, right? So if there is like, suppose that this is connected here, right? And like, the ultimate destination IP is the prefix or IP address within UCSB, right? And it is advertising routes on behalf of UCSB. So when the traffic comes here and it will match on 16.2./16, right? Then it will say that the next hop IP that I know is of this R2, right? So it will say that, okay, like, you should go to whatever the IP address of R2 is. Now the packet needs to know that how can I reach to this IP address, right? Because like, what is the, like, when it goes to the layer 2, it needs to know what is the physical address of this IP address. So that is where the address resolution protocol comes into picture, right? So it translates that for every local IP address that you have to reach out to, there should be a MAC address associated with it, right? So it will use the ARP table. So this in general is called FIB, right? So this is basically forwarding information base of FIB. That is the, like a simplified match action table in the routers. Then it will rely on a ARP table, which is mapping the IP addresses to the MAC addresses, right? So logically, this is, connected to another table, which is basically next hop and then MAC. And MAC, which is destination MAC, right? So I'm just using a simple DMAC here. So for R2, there will be some R2, MAC address, right? So let's call this as IP of R2, and this is the MAC address, right? So this is what a packet needs to know. When the packet is leaving R1, then its destination MAC address in its layer 2 header will be set to this MAC address, right? And the destination IP is still the same, right? Okay. So now the packet will go to switch, and then whatever switch does, then it will go to the R2, right? Now, the original question that I posed was that, is there any field that is reusable here?
Since it just needs to make it to the SDX router, it doesn't actually need the MAC address R2.
Right. So I would treat this as something which is reusable, and rather than actually advertising the actual MAC address of R2 to this R1, I can just advertise any virtual MAC address, right? And that is the key concept or key mechanism that SDX used to piggyback. Like, so if this switch, like, basically, let's try to understand how ARP works, right? So R1 will send a request, say like, tell me what is the MAC address for this IP address, right? That is a request. ARP request will be sent by R1, and it will be broadcasted in the network, right? So if there are other participants, they will also receive that ARP request. But technically, all this is going through the switch, right? So what this switch can do is it intercept this request message and say like, okay, you don't need to know the physical MAC address of R2. I will tell you a virtual MAC address of the R2, right? And then I have, how many bits do we have in MAC address? 32 or 64, 128, how many? 48. Okay. So you're right. So like, so that is the number of bits that we now have available to us to encode the information about these participants. Now I think like that should give you a sense that, we were looking at a setup where we can add hundreds of bits. We only have few tens of bits available. So even though this approach that we discussed so far makes a lot of sense, but we still are short of space that we can use to encode this information, right? And to address that problem, what these researchers did was that they came up with some new encoding scheme, hierarchical encoding, where they just figured out that if you just spend 1 bit per participant, that's a bit wasteful. So what you can do is that rather than like having this type of flat structure in place, you can have a hierarchical structure, right? So you can maybe first group all these participants that have similar forwarding behavior with each other into cluster 1, the other on cluster 2. So you have 2 sets of encoding. First will be matching on the ID of the cluster, and then it will have this bit mask approach within that cluster, right? So it enabled opportunities to decouple decisions from participants that have nothing, like say for example, there will be participants that are advertising completely different set of prefixes, and you will never need to have them all concurrently together, right? So it basically identified those opportunities, and it basically developed this hierarchical encoding which leveraged that observation, and from using that observation, it was actually able to compress for 500 plus participants. It was able to compress all this information within 33 bits, right? So that now we know that 33 bits is something that we can easily fit within the MAC address, and that was the key enabler of how all this was possible, right? The challenge, this is not a completely solved problem because now the participants have increased, right? So this research work came out in 2013, 2014 timeframe, and IXPs are still exploding. I don't know the current number, but I know for sure that a couple of years ago, whatever encoding scheme this research artifact came out with, the number of participants exceeded that. So that's an open problem out there. More innovation is needed to make sure that SDX is sustainable as the number of participants are growing. Of course, what you can do is that you can partition the problem. Rather than having 1 switch, you can have 2 switches, and then decouple the problem. That's how the IXPs are actually trying to apply SDX in real world. But the original encoding scheme has its limitation, that there is a cap of how many participants it can support. So take this 33-bit number with a grain of salt, right? So it is contextual number given the set of participants that it used for its evaluation. And now in real world, we have more than thousands of participants, and this scheme as it doesn't really work. Okay. Any questions? All right, so I think I have this slide which talks about the mechanism, but I don't think we will have time today to dig into that. So I'll cover that in the next lecture. I'll just quickly jump to this result. So if we so 62,000 is the number of rules or policies that total have been expressed by all the participants, right? So basically for this evaluation, these authors came up with a mechanism of synthesizing policies for different participants, and then they used a baseline for 62,000. So these are the original number of rules that are required, right? If we do the naive stuff where we are matching on all the prefixes that we were discussing earlier, then this scales up to 68 million. That's very, very expensive. What SDX was able to do was it was able to bring this down to 65,000. Now you note that it is of the same order as the number of rules, which is expected, but you might see that it's more. So why is it more? If we were doing one-to-one mapping, then it should be just the same, right? But we are not doing one-to-one mapping. We're using the hierarchical encoding, right? So because of that hierarchical encoding, there are a few extra rules that you will have redundant for a particular participant. That say cogent, it might not belong to just one cluster, it might belong to 2 clusters, right? So that is the cost that we have to pay, that with this hierarchical encoding, that there will be multiple clusters to which a particular participant might match. The goal is to make sure that you cluster things so that the overlap is as low as possible, but it is possible, right? So the difference of 3,000 that you see here is actually a reflection of the redundancy that we have with the hierarchical encoding, right? If this was not the case, then we would just expect them to be the same, right? But that's not really the case. All right, so I think in the next lecture, we will discuss the mechanism a bit more before we transition to the next set of discussions. Maybe this is a good time to transition to some questions. Any questions, confusions about the scheme? Yeah.
So if a link is only ever between 2 devices to begin with, and that device is identifying which port it needs to route back into, what's the port of back addresses to begin with?
But this is layer 2 routing, right? So it's not always one-to-one links, right? So there will be a switch and there will be multiple participants, as is the case in SCX as well, right? So there will be multiple MAC addresses to which it can be forwarded.
Yeah.
So if you're getting rid of the next MAC address, like how does the switch know where to send it to?
Switch is the smart person here, right? So it is not the one who's getting fooled by the MAC address. It is the one who's setting up the MAC addresses, right? So switch is connected to the SDX controller. SDX controller has all the mapping of, for these pair of participants, what are the MAC addresses that we should be using.
So do you reuse the next MAC address in the order gate?
Yes.
Okay.
Right. So I think that's a good question. We are not removing this field, right? We're using it, but we are replacing the MAC address. When it is leaving, we're using a virtual MAC address, right? We apply the rule, taking that virtual MAC address into consideration, and then decide that what is the next hop to which it should be forwarded, right? It might not be R2 because of our policies. It might be R3 or some other routers as well, right? So that is the reason we are, first using virtual MAC, but right before it is supposed to leave, then we have to set the MAC address back to the physical MAC address. Otherwise, the device will not be able to recognize it.
And then, sorry, is it the FortiGate router's job to encode the hierarchical encoding, or is it the switch's job?
Switches, right? So border gateway routers will do whatever they know to do, right? So they know how to run this type of table. They know how to run this type of table. That's it. For this table, they are relying on ARP responses. So when they send the ARP request, they rely on ARP responses. What SDX does is it intercepts those requests and crafts, those responses such that rather than physical MAC address, it will be a virtual MAC address. You have a question?
Yeah. So that switch is turning a physical MAC address into a virtual MAC address so that we can do some kind of internal routing.
Right.
But so is another switch later on going to turn it back into a physical one, or is that same switch going to turn it?
Yeah. So that's a good question. The same switch will do it. Switches have multiple, as we saw, right? So there are multiple stages of processing in a switch. So one processing stage will be used for matching on this virtual MAC, and right before it is leaving, then there will be a out table, which will be changing that virtual MAC to physical MAC so that packets can be read correctly.
But if that same switch is turning it from physical to virtual and then virtual to physical, why doesn't it, when it's matching on that virtual MAC address to give it some other metadata or something like that, why can't it just use the physical address if it is
so I think
it has a mapping between physical and the virtual is something else? Why doesn't
yeah,
physical
but those decisions are completely decoupled, right? So so basically virtual MAC is giving it this flexibility to check on the reachability attributes, right? So it's a different functionality that it is serving, and then it is translating that we'll discuss them, the mechanisms are due for the next lecture, but I think it's going to translate that into an abstract MAC address from first table to the next, right? So it uses these reachability attributes and then translates into a virtual representation of say R2, right? And then the final table will be matching on that virtual representation to map it to a physical representation, right? So then the number of entries that we have for match action rules here for MAC address is of the order of number of participants. That's not a problematic thing, right? What is problematic is to have the information for all the participants and their prefixes at the first place, right? So now they are using this trick to replace prefixes with the MAC addresses, this reachability bit mask, which is added as the virtual MAC here, and then they're just flipping it back to the physical address before the packet moves.
So is the virtual the thing we're putting into the MAC address, the virtual MAC address, whatever, like a combination of source and destination and all these different things so that it matches in a particular table that we want it to be?
No. So virtual MAC address is only representing or capturing the reachability attributes that we were discussing, right? So it's basically a bit mask, compressed bit mask of information about what are the right set of participants to which this packet can be forwarded, right? So it is capturing that information. How does switch figure out that it is coming from this R1 and what policies need to be applied? So that is based on the import. So packet, when it comes in, it has an import that which port it is coming through. That's how we know that which set of policies needs to be applied first, right? So we'll I think these are all interesting questions, and we'll get into the details of how exactly this is getting realized. In general, just to give you a perspective, that there are 4 different tables that will be applied in this switch. First will be inbound table, then that will just match on the import and figure out what set of policies need to be applied, right? And then there will be participant specific tables, right? So there will be two set of participant specific table, which is like inbound rules, outbound rules. And then there will be final table that will be making sure that the final packet that is going out to the wire is compatible and is compliant with all the protocols out there. Any questions? I think this last discussion has been a bit abstract, but don't worry, we'll be digging into the details in the next lecture, and we'll understand how exactly the mechanisms of different protocols work here. All right. So, I think this lecture must have given you a perspective of one way in which the software-defined networking can be applied in a context that is not data centers, right? So we learned about data centers in the previous discussion about this NVP and multi-tenant data centers. So this is a non-data center setup, right? And in the next lecture, immediately we'll learn dig into the mechanisms. But as we progress, we'll be talking about the wide area networks, right? So basically the network that is connecting different data centers and how software-defined networking can be useful and transformative there. That's what we will cover as we proceed here. Okay. All right.